All right, so tonight we're going to take a look at two new classification algorithms. The first is KNearest Neighbors, usually you just call it KNN, and the second is support vector machines, and it's usually just abbreviated SVM. So we'll start with KNN. It's probably the most easy of the two and the most straightforward. So I have a little GIF here. I might have to go back to see it. So basically we have two different classes. We choose a number of local points, so the closest points to it, and we see what class all those different points are. And whichever class has the highest number, basically we say that the new point is most likely that class. So you usually pick an odd value so that there's no ties. And you can basically try any value from 1 to really anything, depending on how big your data set is. But depending on how many you choose, as seen in this GIF, you might get different classifications for the same point. So with 5, the 5 nearest, we can see that it's classified as a green dot. But then on this next part, if we go up to 7, it includes these 2 red ones. And then in that case, there's 4 red and 3 green, so it would be red, or they call it brown for some reason. It definitely looks red to me. But so that's the basic idea. It's pretty intuitive and easy to understand. So we're just going to start working with it here. So to import it, again, comes from sklearn. Basically, all the machine learning models you use come from sklearn, at least the ones we've done so far. And now we're going to make a data set and use a KNN on it. So this will make a classification data set, and then we're just going to do a train test split so we can see what kind of accuracies we get on the test set. So we'll run that. And now this is just going to plot that data. So there we go. All right, so the lighter orange color is like class 1, the blue color is class 2, and then this darker red-orange color, those are like the test points, so the ones we're trying to classify. So I mean, just looking at this, for example, this point up here, if we have basically k equals anything, it's going to be classified as these red points, and kind of same with this one down here. But this one in the middle, it's kind of more of a mixture, so that one could go either way depending on what we choose for k. So we'll go ahead and fit a classifier. You basically do it the same way that you do all the other models for sklearn, and then do the prediction the same way. The main parameter you'll change is the n neighbors. And so we'll just start with 1 and kind of see what happens. So we got our prediction. We can import accuracy score so we can check that, and then print out the actual predicted and then the true values as well. So we can see we misclassified 2 of them and got 3 right. So that gave us a 60% accuracy. And then if we go ahead and run this, this is going to show us basically where all the boundaries are with a k equal to 1. So with k equals 1, this is how it divides up the data. So the yellow dots represent all the red space. So any test points in the red space would be classified as the yellow, and then oppositely for the blue and the purple dots. So we can go back and change our neighbors here to say 5. I'll run this again, and that time we got 100% accuracy, so that might be the best option. And if we run this again here, we can see it split it up a little bit differently. It seems to capture most of the points. There are some that are misclassified, but this is kind of a difficult to separate data set. So that's probably the best we can do. The way to kind of see what value of k is best is to basically run through values from 1 to whatever limit. In this case, I do 30. So this will basically build a model for each value of k from 1 through 30. It will fit it to the training data, predict using the test data, and then just store all those scores. And then I'll just plot it so we can see what happens. So in this case, it seems like once we get up to 3 or higher, we get 100% accuracy. But if we go back now and make our data set a little bit more let's see, a little bit more difficult. So if we lower this separation, and then we'll go up to 1,000 samples. So we can see what that looks like here. So it's kind of more mixed now. There's not really, groups off to the side that are all one color. So this will probably be harder. The default is actually 5. So if you don't put anything in there, it'll have k equals 5. So we can try that. We got 74% accuracy. Not terrible. You can see how it separated it. So this one's a lot more difficult to separate, as you can see. It kind of groups those purple dots in like a middle band, but it's kind of hard to see how it divides it up in the center because the dots cover it up. But if we run this now, we can see how the accuracy changes on our test data as we change the value of k. So we get the 74% accuracy, it looks like, at, I'm going to say that's 5. Yeah, 5, and then maybe 6. You'd have to like print out the actual scores to see the exact number maybe, and then this one looks like at 20 and also 15 through 17. So any of those values would give you the best score. Typically you want to pick the lowest of those values. KNNs are really computationally expensive the more data points you get, because basically if we have a point we're trying to classify, like say this red dot here, we have to compare it to every other single point and calculate the distance. So if you have, 10,000, 100,000, a million data points, that's going to take a really long time, because in this example, we have maybe like 100 in our test, but you could have 1,000 test points. So it can really, kind of spiral out of control there. And yeah, so that's basically KNN in a nutshell. It's pretty easy to work with. It's not the most popular machine learning model, but it does get some use, and sometimes it is the right option. And here at the end, I'll kind of do a comparison of the different models to kind of show you when you would use one over the other. But before we move on to SVM, does anyone have any questions? Did this
Matt, I have a question. So
Sure.
When you make the test and train data set, you have a parameter class sep equals 0.1, like above. Yeah, what is the class separation?
So that's basically how far apart it'll make the classes. So here it's pretty low. I can put it up to something like 10, and you'll see what happens. So this is it with a small decimal, and with 10, it really separates them out.
And here, so the blue and the yellow, is it the classes that based on the train data set, and the red are the test?
So the light blue is like class 1, and then the orange is class 2, and then these darker ones are in the test data.
Okay, got it.
Yep. And yeah, this is just from sklearn. They have a bunch of these where you can make mock data sets. And there's a bunch of parameters. You can have multiple classes, more than 2, different features, change the number of samples. It's actually kind of fun to mess around with, and it can be a way to kind of get some practice in building models too. So definitely check that out sometime maybe. All right. Anyone else have any questions on KNNs? Nope. Okay, we'll move on to SVMs then, support vector machines. These are a bit more complicated, a bit more difficult to intuitively understand. Basically, the main idea is that we have 2 classes here, and we want to draw some line that can separate them the best way. So that on one side of the line, we predict one class, and on the other side of the line, we predict the other. So here's some of the lines we could draw. But perhaps the most optimal line, or the optimal hyperplane, which we'll talk about in a second, is this line here, because it basically maximizes the distance on both sides to where the classes are located. So this gives us kind of the best division between these 2 classes. So with SVMs, there's a few different parameters and components that are kind of important. So the first is regularization. This is called C. It's a parameter you can change. And basically, the lower it is, the better you will, the more likely you'll be to misclassify, but basically the straighter your line will be. So if we have the low regularization value here, you can see it's basically in the middle between the 2 points, the 2 classes, but we did misclassify these 2 black dots. On the other hand, if we put a high regularization value, we can see that it tried really hard to make sure we divided it correctly and not misclassify any. But now the boundary between the 2 classes is really small in most places. So in that case, we're probably overfitted. So the low regularization values can kind of help to prevent against overfitting. But sometimes if it's too low, then you can actually underfit. So it's kind of something you have to balance and play around with. There is like a default value. You can kind of just go with that, but it is there to tune as well. And that's called C. I think that's what you would set it as using the sklearn. But if you look it up, C is usually what they refer to it as. So the next is gamma, which is basically how much closer or farther away points should be considered. So if we have a low gamma, we're going to consider points far away from our hyperplane line between the classes. And then on the other hand, if we have a high gamma, we're only going to consider the points really close to that hyperplane line. So this can kind of change how we come up with that hyperplane line, how we divide the classes. It's kind of just something else you can tune, but you want it, somewhere in the middle where it's balanced, basically. The next is the margin, which is just the separation between that hyperplane and the support vectors. So on the left here, we have a small margin, and then on the right, we have an example of a large margin. So the support vectors are actually the lines that are basically right up against the classes. So there's one on each side, and then the hyperplane is usually kind of equidistant between those 2 support vectors. So the closer those support vectors are together, the smaller margin we're going to have from the support vector to the hyperplane, versus where they're further apart, then we're going to have a wider margin. And overall, the goal is to have a wide margin because we want to separate them in the best way possible. So another part of SVMs are kernels. So traditional SVM is just linear, so it will just do one single line to divide classes. But sometimes we have data like this on the left, where we have this inner ring. This is one class. It's kind of hard to see the colors because it's small, but then the outer ring is a second class. So we can't really, draw one line through this to divide it up. So what kernels do, they basically transform the features into higher dimensional space. So if you look over to the right, it basically moved up all the outer radius points and kept the ones in the center more towards the bottom, but it basically projected it into 3D space. And now you can imagine we could have a plane basically cutting through where this division is. And in that case, we could divide them really easily. So there are a couple of different kernels. There's like polynomial kernel. This is RBF, which is radial, I forget the acronym. Let's see if I have this. So this is the library, the documentation. So the default is RBF. It's basically like a radial transformation. So like it'll pick a center, and points farther away from the center basically are weighted to be moved upward, whereas points close to the center are weighted to be closer to the bottom. But there are other kernels, such as like polynomial. So it can square your features, it can cube them, and there's also sigmoid. There are some others too that you can't actually implement here, But generally, RBF is going to be like your go-to. It is the default. It can usually handle most shapes, but depending on how your data is, you may have to do some research and look into these other ones. But in general, you're going to find the best results with RBF. Sometimes you can use linear if your data looks like this, and you think you can divide it with one single line. All right. So we'll go ahead and look at a data set here and see how we use SVM. So go back. There we go. All right. So again, like before, we have our two classes here. We have our orange class and then our blue class. And then the darker points are like our test data. So we have to find a way to divide up these two classes. And just like before, we can't really draw a straight line. So at first, I'm going to use a linear kernel just to kind of show you. And I'll print out the accuracy score of it. And this is fitted and predicted like the same way as all the other models. So with a linear kernel, we only get 48% accuracy. But if we use the default, the RBF, we actually get a 98% accuracy. Because again, what it's doing is taking these kind of flat linear features, projecting them into a higher dimension, which allows them to be separated. All right, so before we go into like a summary here, does anybody have any questions about SVMs?
So RBF, like how many higher dimensions? You can do like I know you can do square or like different polynomial terms that the function just decide for us.
That's a good question. Let me see if it mentions that here. I'll have to double check how it actually does it. If there is some kind of automated thing where it picks the best.
It seems the degree is default 3.
Okay.
So degree of the polynomial kernel function is 3 by default.
Oh yeah, there it is. Okay. So that's only if you choose the polynomial though. I think RBF, it's kind of like a set thing. I'm not sure, well, like here, for example, it's in 3 dimensions. I'm not sure maybe if it's always in 3 dimensions, to double check. But yeah, if you do polynomial, then you can specify the degree. So sometimes you might have to go to a higher dimension to have it be separable.
And the accuracy score, what is the ideal range if we do classification?
I mean, 100% is going to be your best. But you also have to, look at other things like recall and precision. You can look at the F1 score. Usually you want to look at a couple, but for this example, I was just doing accuracy. So 98 is really good. And I mean, that makes sense because you can imagine if we lift this blue ring up in like third dimension, like out towards us maybe, then we can imagine we slide like a sheet of paper between the orange ring and the blue ring. That's kind of the hyperplane that the SVM comes up with.
Yeah.
Yep. And so SVM actually works using gradient descent, which you'll remember from linear regression, also logistic regression. So it has a loss function. It's a bit more complicated than linear regression or logistic regression, but you still might want to look it up. I think the curriculum goes over it a little bit, but it's probably worth it to understand a little bit. It's kind of outside the scope of this lesson to go through it all. But it would probably be smart to at least be somewhat familiar with it. And yeah, any other questions on SVM before we do a summary?
Yes. So how can you, by either visualizing the data or some other indicator, look at which kernel you should use? So do you just try all of them and see which one works the best? Or is there a way that you can kind of have a rough idea of which one's going to work the best before you try them?
I mean, since there's only 4, you could just do a grid search and try them all. There is probably some way to kind of see if you should use one over the other. But you'd probably want to just start off with the default. And if that doesn't work, I mean, you only have 3 more to try. So you could probably just do the grid search with each of those.
Gotcha.
Yep,
and your scatter plot, the np dot h stack. Yeah, can you just explain how you realize this? Yeah.
Yep. Okay. So I have my train and test split up, but I want to show them on the graph together. So I show all my data points. So I basically stack them together. My data set has 2 features. So this here gets the first column, the first feature of the train and the test X. And then the second one is getting the second feature, the one for the column. And then this here, so basically to print them all as different colors, if I took my train, it would just be 0 and 1s. So I make all of the Y values. Actually, let me see here. Okay, so this is actually all of our Y values, which are 0 or 1. And then, yeah, okay, so that's for the color. So that determines if they're orange or blue in the train. But then for the test, I want them to be a different color. So I have to give them a different value. So this makes basically a list of 2s. So normally like the blues 1 and the oranges 0. But then these darker ones are given a value of 2 so that it gives them a different color basically. Does that make sense?
So the first one, scatter, I thought we are stacking 2 classes, but here is stacking 2 features.
So these are this is column 1 from the train and the test, just kind of stacked on top of each other, so that we have all the of the first feature. And then it's kind of the same thing for this, only it's the second feature, the second column. And then the color is the class. So our Y values are the class. So for this example, it's either a 0 or a 1.
Oh, okay.
But for the test points, I want them to be a different color. So I make all of them have a value of 2 so that it treats them as a third class and gives them a different color.
Okay, that makes more sense.
Yep. All right, let's go back out of here. All right, so this is kind of a simple classification guide when to use each algorithm. So we've kind of done 4 classification algorithms so far. We have logistic regression, KNN, SVM, random forest. You also have ensemble methods. Those are kind of something you do like as a second step. You know, you can combine some of these or do some kind of boosting. But for these kind of baseline models, we have 4 options that we've learned so far. So for logistic regression, if you have a binary classification, so predicting 0s or 1s, true or false, you only have 2 classes, logistic regression is usually the best option. When you have more classes or when you still only have 2, all the other ones are still applicable. But KNN since it does get really computationally expensive, it's really best for when you have about less than 10,000 rows in your data set. So for smaller to medium data sets, and then also not many features. That kind of adds a lot of complexity as well too. So in that case, if you have a low to medium number of data points and you have actually high dimensional data, so 50, 100, or even more features, then SVM actually does really well. It handles the high dimensional data a lot better than KNN. And then if you have categorical features, more than 10,000 rows in your data set, and you have high dimensional data, random forest is probably going to be the best and the fastest. Random forest will pretty much always work. It's a good out of the box, just to throw a model at something. But it's not always the best option you can do. And there's kind of a lot of tuning too. You remember with the random forest lesson, we had that dictionary of parameters we could change, the depth of the tree, affecting how likely it is to split, how many points it has to have to make a split. There's a whole list of parameters, whereas KNN only has one parameter, K, and SVM has a couple with the regularization and the kernel, but still not too many. So these are a lot easier to grid search and kind of tune. Random forest is a bit more difficult to tune, but it also is the most robust and can pretty much handle any data set for classification. So this is kind of a summary, like a cheat sheet. So if you come across a data set and you don't know where to start, you can kind of follow this. There are other cheat sheets like this. There's some flow charts I can send you, or if this, go to this model. If that doesn't work, go to this one. But yeah, that's basically in a nutshell classification models that we've learned so far. So with that being said, we're going to do an activity here. So like usual, there's a CSV file with some data in it. You're going to build a classification model. So there's a couple steps here to go through. So first, you're just going to load it in, do a train test split, use this test size, and then this random state, just so everybody has the same data. And then you're going to look at the data and kind of following the guide, decide which one might be best if you had to only go with one. But then you'll actually fit all three, KNN, SVM, and random forest. And I'm actually going to have you time each one. So I have the skeleton here. You basically fill in the training in the center here. You can copy this 3 times just to see how long it takes to give you an idea of the complexity. So you're going to fit all 3. And then you're going to make predictions, calculate the accuracy and F1 score, and then kind of decide from that which one you think performs the best. And then lastly, you'll just choose one of those, perhaps the one that did the best out of the gates, and then you will do a grid search, cross-validation on it. So you can go to the documentations, check out what params you can choose and change, and then make a dictionary of those params you want to try out, fit the grid search model, and basically see how much you can improve it. So that is the activity. Any questions before we start? Nope. Okay.
Alrighty, we just started off importing the libraries, importing the data frame, setting the random state, and doing the test size on our features and target, looking at the number of rows, features, and classes. And we thought it would be good to do the SVM model. Here we made 3 different models, looking at KNN, predicting which K to use here. So we figured 65 is the highest. So here we did our start time, end time to see how long each one took to fit. And I just passed them into a data frame to look at the time. It's like KNN fits the fastest RBF takes the longest.
With that being said, though, what's the caveat with the KNN being quick to fit?
Oh, KNN's quick to fit, but it takes a long time to predict. So the more features you have, the times like increased exponentially.
Yep.
And here we were just looking at our predictions to get the accuracy and F1 scores. So for each model, we did the prediction and calculated the scores. I just appended them to the data frame. We used labels as the categories for the target and did an average of none. And we just printed out for each model the F1 score for each class here. Then we did a grid search to find the best hyperparameters using a dictionary and listing out the different combinations we wanted to try out. I used 20 number of jobs to do them at the same time. And we got the same as our base model. So if we would have included more parameters here, we probably would have got something different here. And since we used the same base models, we got the same accuracy as we did earlier.
Yep. And what we mentioned when we were doing the grid search is that you always want to include the default values too, just so that if the base model is the best set of features, that you do end up with that in the end. So it's good to keep in mind. And yep, so now you guys have kind of a toolbox of classification algorithms, and hopefully you kind of learned when some are better than others. And yeah.
Alrighty.